next speaker and also the last speaker for the day is Ghosal from Brandeis, who will talk about fractal geometry of the Parabolic Anderson Model in high dimension.
Thank you. Thank you very much for the invitation. It's so nice to see all of you here for this 2-week-long conference. And I'm going to talk about this work came out last year on fractal geometry of Parabolic Anderson Model in high dimension. I'll tell you what this Parabolic Anderson Model is and what do I mean by high dimension. But I should mention that this is the joint work with Jaeyun Yi. So during the time when we were working, he was a postdoc in Kias in South Korea, and now he's a postdoc in EPFL with Martin Harrer. Okay, perfect. Okay, so this is the plan of the talk, and I'll give you this definitions of the Parabolic Anderson Model. What does it mean? And then I'll go to this fractality. So what do I mean by this fractal geometry or whatever for this Parabolic Anderson Model? And I'm going to talk about this specific dimension for our Parabolic Anderson Model. So just to give you a spoiler alert, Parabolic Anderson Model, the one that I'm going to talk about, is a stochastic partial differential equation. So there is a spatial dimension involved in it, and there is a time dimension. So the spatial dimension, I'm going to consider 2 and 3. And that there is a time dimension, that's why it's called like 2 plus 1D and 3 plus 1D. And we'll talk about why I'm not going to talk about this 4 plus 1D or anything higher than that. Depending on how much time I would have, I'll discuss the proof ideas of the result as well. Okay, so I'm going to start from a slightly different angle, and something like probably not mentioned in the title. It's maybe somewhat related to some of this time inequality theory, which is the other part of the conference people are familiar with. Something called like Anderson localization. And this is a phenomenon which appears in like understanding conduction of electrons and crystals. So there was a time that when people were trying to understand this transition of this crystal from metal to insulator, and there's a lot of this theory people are trying to propose, but none of this were working. So Anderson, who's a physicist, were trying to sort of like understand what's going on there. So he's trying to understand this through wave mechanics of electrons. So when you try to model the electrons as a wave, you better understand it as a sort of eigenfunction of some operator. So if we take this Laplacian as an operator for these electrons, then Laplacian will have this eigenfunctions, cosine and sine. So it's like infinitely extended. So it would be sort of perfect example of conduction or perfect conduction. On the other hand, in crystals, you would see like a lot of impurities, and the way to model this as like sort of a noise. And if you think noise as an operator, the eigenfunction of that would just be a degenerate function. So what Anderson was like, the plan of Anderson was like to just put these two things together and try to explain what is going on in these crystals. So the Anderson Hamiltonian, which people now like used to call it, is just this Laplacian plus this this noise parameter, this noise function, which you call it as a potential function. So his proposal was that this, if we consider this eigen functions of this particular Hamiltonian, then they should be like exponentially localized in the sense that like there would be some degenerate, there would be some random spots over which this eigenfunction would be localized in the sense that it would be exponentially decaying around those points. Now this was the proposal, and he was able to prove it for like this specific choice of this noise, and in the lattice, in the discrete case. But later, this has been proven in like a higher dimension and many other choices of noise. And this story has been going on for like almost like 50, 60 years, and it spilled out like there's a lot of methods which people have like were able to kind of come up with, and it's percolated in other branches of math as well, and not only just as restricted to this Anderson localization, but in probability and other fields. And there many people were involved, and Jean Bourgain was like one of the stalwarts in this field of like proving this Anderson localization for quasi-periodic Schrodinger operators. But the thing that I want to sort of like understand is this particular question that we focus on this noise being white noise, and what we want to focus on is this how this eigenfunction would look like, and how do we measure some sort of like this density of this random spots over which they would be localized. Now, you may have already wondered that like my title of the talk had like Parabolic Anderson Model, and what that has to do with this Anderson localization. And that's what I'm going to explain in this slide. So, and Parabolic Anderson Model is just a dynamical version of this Anderson Hamiltonian. So you just like add a time derivative of this eigenfunction of this Anderson Hamiltonian, and equate that with this Anderson Hamiltonian acted on this eigenfunction. So then you get this Parabolic Anderson Model, or this stochastic PD, which we call it, like a Parabolic Anderson Model. The particular initial data, when there is a stochastic PD, there will be initial data, and the one that we would be interested in is this delta initial data. Now, this also had like a parallel lives. This model has a parallel lives in the sense not only just people are interested to study this through this lens of Anderson localization, but also this has like physical importance in the sense this were used to model this random mass transport in random media sink and sources, and many other things like the polymer model. You just have to sort of like take a. So here, one thing I just want to point it out this noise is here space dependent. I did not add a time dependence in the noise. You can add a time dependence, and then it would be sort of like a perfect model for modeling this polymer model. Now, one of the nice things about studying this Parabolic Anderson Model is that you can directly relate that with this Anderson Hamiltonian in this following way. This is like the spectral decomposition of the solution of this Parabolic Anderson Model. So what you do is that you take this eigenfunction of this Anderson Hamiltonian and eigenvalues this lambda k, and you take this kind of linear combination in a particular way. You just take this product of this eigenfunction, weight that weigh that with this exponential of t times lambda k, sum over all these eigenvalues. That would give you this representation of the solution of the Parabolic Anderson Model. Now, this thing will connect one of the very important property of the Parabolic Anderson Model with this Anderson localization. And that property is this called like intermittency. Now, you may not have heard intermittency, but while coming here, you probably already have seen what this intermittency is. So people were studying this intermittency for like 30, 40 years. There are various definitions of this intermittency. One of the geometric way to viewing the intermittency is the following. So if you probably, when you're landing in Mumbai airport, you have seen this landscape of this Mumbai city. And it's almost like there are like valleys where there's like small houses, and there are like large houses. So these are, you can think of it as peaks, these large buildings as peaks of this landscape, and these valleys are just valleys. So if it happens that like in a landscape of a stochastic process, the peaks are kind of quite long, And if they're separated by a wide distance, then the system would be called intermittent. Now, what happens here is that if you believe that this Anderson localization happens here, the eigenfunction would be localized in a random spot, and they would be separated by a long distance. And when you weight that with exponential of t times lambda k, that will make this peak size higher there. And this Anderson localization by this representation would lead to intermittency for the parabolic Anderson model. So if you can prove Anderson localization, it proves this intermittency in a very strong way. Nonetheless, this representation gives a kind of a very handy way to study parabolic Anderson model as well. But we will try to sort of investigate something else, not exactly this localization or intermittency. So this is the goal of the talk. So what we do is that we'll fix the t parameter, and we would ask that what would be the scaling for the peaks that I was mentioning. So essentially, this would be sort of like, if you believe this Anderson localization would be sort of the weight this location of this eigenfunction would get, and how frequent that they occur. How would you measure that, like kind of a density of the peaks? And you can ask the same question for this spatio-temporal profile as well. I will try to answer that as well. Now, this is a problem that I am telling to you, but why you would be interested in kind of knowing the answer to these questions. So this is something I'll try to clarify in the next 2-3 minutes. So the motivation for studying this kind of problem comes from a series of works or kind of like ideas which were propelled in this physics literature. So physicists were studying this this intermittency in general for a more kind of wide sense, and one of the ways they're trying to do like a lot of simulations. This is like a picture of a simulation taken from a PRL paper, came out in 2000. So the simulation is about a stochastic system where the noise comes in a like sort of a multiplicative way. Let me just explain you what this multiplicative noise means. So here you see this, the noise is multiplied by the solution of this parabolic Anderson model. And this is sort of the signify the multiplicative nature of this white noise. Now, when there is this noise is emerging as in a multiplicative way, so they focus on a system not necessarily parabolic Anderson model, but the noise is multiplicative. So they were looking at the peaks, and if the peaks exceed some threshold, they color it as white. And if it exceeds some, if it's below that threshold, it's colored as black. Now you see, like there's this white and black region has some like a laminar structure, but then they're often nucleated by some neighboring kind of turbulence-like structures. And these turbulence-like structures are varying sizes if you kind of scan from one end to other end of this picture. So this varying sizes of this turbulent structure is coming out because of one specific property that's called like a multifractality. So in other words, what the idea that physicists were like proposing is that this multifractality is the one which kind of marrying these two things together, this localization and this intermittency. So the goal of the talk is that how a multifractality, we can detect multifractality and to use that to explain intermittency of the system, especially for the parabolic Anderson model. Any question up until this point? Yes.
So you said something about multifractality. So what are the different dimensions and what kind of connotation do they have? The different fractal dimensions?
Yeah, so I'm going to sort of mathematically formulate what this multifractality means. It's kind of like, for till now, it's very vague, right? Like I haven't given you any sort of definition of multifractality, I'm going to give you that. And through that definition, we'll sort of study like if you can prove any multifractality for the Parabolic Anderson model. Okay, so the next step is to go towards this fractality or multifractality, as I was telling you. So for that, we need a notion of this fractal dimension. And this is not a natural fractal dimension I'm going to sort of use here. What I'm going to use is something called like a macroscopic fractal dimension, or Hausdorff dimension. This is like introduced by Barlow and Taylor in 1991. And philosophically, if you want to think of it or relate it with this usual notion of fractal dimension, so if you take a like a stochastic process, if you zoomed out the stochastic process and asked like what is the usual Hausdorff dimension, that would be equivalent to this macroscopic Hausdorff dimension. But it needs a formal definition. I'll just like give it to you here. So what we do here is that we'll take this a geometric object, it could be in any dimension, and we'll try to sort of like divide that geometric object by a sequence of growing squares. So for instance, here you can see that there's this inner square here, which is like this e power minus n minus 1 to e power n minus 1 to the power d, and the outer one is this e power n minus e power n to e power n to the power d. And this the region which is kind of like confined between the squares, the shell type region, is this green part of this geometric object. So this geometric object is a union of this blue, green, and brown region, and the shell type region has this kind of green part. So what we do is that this intermediate region, we'll try to sort of cover it with kind of rectangles with side lengths is at least 1. It could be something else, some constant, but for now I'll just set it to be 1. And with this coverings, we'll just compute an object like this, which is the infimum of this maximum side of this rectangles over e power n to the power rho, sum over all such kind of rectangles that I use for coverings, and I take the infimum over all such coverings possible. You might notice that I'm introducing a new parameter rho here. It will play some role. And one thing to notice here is that if you keep on increasing this value of rho, this whole thing will going to get towards 0. Okay, so
is the assumption that e to the n is the size of the biggest rectangle?
yes, that's kind of why this has this index n. Okay, so the row dimensional Hausdorff content would just be equals to the sum over all such new rho n. So you take this for this nth shell, you compute this new rho n and take the sum over all such new rho n. So macroscopic Hausdorff dimension of n is that E would just be equals to the infimum value of rho, such that this row dimensional Hausdorff content would be finite. As I was saying, that if you keep on increasing the rho, it will start to get towards 0. So there will be a finite value of rho, or it would take a finite value, stop there. And I would call it like a macroscopic Hausdorff dimension. Now, just to kind of like relate it to the usual definition of the Hausdorff dimension that we know, so we'll do the exact same thing, or almost exact same thing for this defining this Hausdorff dimension. Only difference is with instead of like growing squares, you'll take the shrinking squares, and that will give you this local version of this Hausdorff dimension. Now, a stochastic process is called multifractal with a gauge function g. There are infinite many scales possible, such that if you look at this fractal dimension and macroscopic Hausdorff dimension of the level sets of the stochastic process correctly scaled, then this level set or fractal dimension of this level sets would be perfectly ordered. Like there would be like perfect inequalities between this. So if you get infinitely many such scales, we call it multifractal. If it's just finitely many possible scales, you get a perfect inequality. We'll call it monofractal. So this is sort of like how we kind of define mathematically how this capture this kind of different sizes of this turbulent sides. Okay, so I'll try to review what's been known in terms of this fractal dimension for 1 plus 1D, because that's the case I'm leaving, so I have to explain what's going on there. So this study of this 1 plus 1D parabolic Anderson model, at least in this kind of for this white noise case, like it's kind of not that old. So it's people kind of studying it like almost like a 10, 15 years from now, and so one of the kind of like the nicest thing was this like understanding this gauge, what could be the choice of the gauge function. So this was done by this Jaeyun in 2014, and what he found out is that like for a large class of initial data, if you take this nfx x, then this logarithm of the solution of the parabolic Anderson model was scaled by t times log t to the power 2/3 would go to this limit per kind of like perfectly kind of deterministic limit, 1/2 times like 3/2 to the power 2/3. Now this is kind of this. This will give you some idea of the gauge function, and then based on it, even like using this proof structure, Khoshnevis and Kim and Zhao were able to prove this multifractality for 1 plus 1D parabolic Anderson model. And their result looks something like this. So what they took is that it again works with a very large class of initial data, and they showed that this peaks of the spatio-temporal parabolic Anderson model is multifractal in the following sense. They take this fractal dimension of this level sets, spatio-temporal level sets, in this particular way. So the choice of the gauge function is kind of hidden in this the way that I wrote. So to understand the gauge function, you have to take this logarithm of u divided by t. That would give you this choice of the gauge function. And what they showed is this fractal dimension is it's bounded by two continuous function of the level that you set, like this beta. So for different choices of beta, which are kind of like not same with each other, you get a different values of this fractal dimension. Like, and you get infinitely many such different values. That's why it would be like a multifractal. Okay, so I told you multifractality, but what can you say anything about the intermittency or localization, for instance, for this 1 plus 1D case? And it turns out it's also been figured out, but quite recently. So there is a series of work by Laura Dumas and Cyril Labbe, who gave like complete characterization of the intermittency or localization in this 1 plus 1D parabolic Anderson model. So when I'm I have to just remind you that this kind of structure or this kind of result already been known when the noise is something else, kind of smooth noise. But for white noise, this was a kind of a really challenging problem, and they were able to kind of sort this out. And kind of the statement of the result is the following. So if you take this eigenvalues, which would be like a pure point spectrum, and eigenfunctions in a kind of a box with the Dirichlet-Neumann boundary condition, then under proper centering and scaling, this eigenvalues would converge to a Poisson-point process. And this eigenfunction would be concentrated in a uniformly distributed Dirac masses and with exponential decaying tails. And they won't be exactly like a degenerate function, but they would be like a function with exponential tails. That's the kind of like the structure of the nature of the statement of Anderson localization. And this, since they were able to prove this region of concentration of this leading eigenfunctions would create this island of the peaks, which is responsible for this intermittency. So it's like these two things together kind of like shows the intermittency as well. Yeah.
Is the rate of decay related to the eigenvalue?
The rate of decay would. Yeah, the location of the. So since you asked the question, so I should mention that there's another notion of localization called dynamical localization, where you're also able to specify like at what rate they're kind of decaying. If it turns out that if you can prove some sort of bound, or which is like independent of this location of the sites, that would kind of prove the dynamical localization for this model. But as far as I know, they were not able to prove that dynamical localization. Okay, so then what's going on in this 2+1D case? And there is one particular result which drags me and my collaborator to this particular case. So there is this very interesting work by Koenig, Perkowski, and Van Zuylen in 2020. What they showed is that if you take this parabolic Anderson model in 2+1D and take this minimum of the solution in a box of length t power alpha, and the supremum of the solution in whole like a two-dimensional plane, then they actually grow almost in a like a same rate, in the sense that if you take this logarithm of this minimum and logarithm of supremum, they have the same asymptotics as t goes to infinity. That is a bit shock for this entire community, because if you believe in intermittency, what does it say is that there is a large peaks and there is a values which are kind of like very low, at a very low level. So the minimum could not be equals to this, like the height of this large peaks. So this result kind of like indicating towards absence of intermittency, at least on the level of this logarithmic asymptotics. That's a bit kind of a shock for all of us. And even like the authors don't believe that it's not intermittent. So, and they're kind of the shocking, or rather weak part of this result is that they cannot prove this this asymptotics when alpha equals to 1, which is sort of like the understood to be the length of the localization for this model. So what we ask is that, like, and it needs a lot of this technicalities to extend to like towards like the result towards alpha equals to 1. So instead of like proving or improving this asymptotics, what we ask is that can we show any sort of like a fractality for this landscape? And that's where we're going. Okay, so this is the result that we are able to show. And this is kind of like proves this multifractality of the landscape. So this first result is for like for a fixed t, and like for just for the spatial profile, and the next one is for the spatio-temporal profile. So what we are able to show is that for a fixed t, and it could be just like it's not a like this fixed t is not random. There's for all t greater than this t naught, this macroscopic fractal dimension of this level sets of this spatial level sets of this solution of parabolic Anderson model in 2+1D case has a very concrete value, and it's not random, it's like a deterministic. So since this value is continuously varying with this level that I set here, which is equals to alpha, it shows this multifractality, because like if you like take this distinct value of alpha, you get a distinct value of this fractal dimension. And some of the techniques that we have used for proving this were able to kind of show another result, interesting result, which is like a spatial asymptotics. So if you fix t, if you scale this logarithm solution of parabolic Anderson model, and by logarithm of x, it converges to a kind of a fixed constant, and irrespective of like irrespective of the value of t that you chose. So and then we have a version of this result for the spatio-temporal profile as well. So you take this kind of level sets. Now this gauge function that I talked about is different than this spatial result. And we are able to show the exact value of this fractal dimension as well. And this is also varying continuously with the level that I set here. We have a version of this result for 3+1D case as well. And we have like spatial and spatio-temporal result as almost in the same nature as this 2+1D case. And this is kind of the special version of the result. So this is sort of like and the summary of the result is that this shows this multifractality in 2+1D and 3+1D case. Now, I think I have like some time, right? Half an hour? Okay, so that's quite a lot of time. But let me just tell, I probably would finish a bit early. Let me just say that like why we haven't gone beyond it, like what stopped us like to go to like 4+1D case. So in this stochastic PD, there is this this kind of hindrance which stopped us like in many occasions, which is this criticality. So in 1+1D for the Parabolic Anderson model, it was kind of easy to deal with because like you were able to compute the moments, and that's kind of what the backbone of the analysis people are doing for a long time. But in the 2+1D case and 3+1D case, the moments blows up, so you cannot actually kind of work with the moments. So that was kind of one of the main obstruction, but we were able to kind of like go over it. But in the 4+1D case, what is still to be done is to make sense of the solution, because that's the critical dimension for the Parabolic Anderson model. And the same problem like resides in the KPZ equation, if you know it, or Young-Mills, for instance. The solution theory, since the solution theory is not available, we're not able to go beyond it. Okay, so the proof ideas. So what I would do is I'd first present you like the main tools that we have kind of used for proving this result that we had. And one of the main kind of tools that we have used is this Feynman-Catch formula, and I'll tell you how does it look like in this case, or what was the kind of challenges associated with it. And the next thing is tail probabilities of the solution of the Parabolic Anderson model, and there is it also involves some challenges, but eventually we're able to kind of get rid of those. And the spectral representation that I showed you. So the spectral representation, as like the way I wrote, gives you like the kind of formula for the solution of this Parabolic Anderson model. There is a lot of things to take out of it, but it's not as easy as you think, as it kind of looks to be. The reason is that the sum involved in the spectral representation, you don't know whether that would be finite or not. So it needs some messages to kind of make sense of it. Okay, so let me give you the idea for behind this upper bound for proving this fractal dimension. So the way it works is I will prove this upper bound and lower bound separately, and each of them has like its own challenges. I'll kind of like tell you how does it look like. So in this definition of this macroscopic Hausdorff dimension, there is this big summation involved, which is summation of this over this summation involved in this Hausdorff content. And along this line, to prove some upper bound for this fractal dimension, what one needs to do is that choose a row which is just above this Hausdorff dimension, which we kind of guess. Then for that particular choice of row, prove that this kind of a big sum is finite almost surely. This is kind of where it reduces to prove some upper bound. It's probably like needs a little bit of thought, but it's kind of not hard to track like where this is coming from. So we had to understand how the sum, like how to kind of tackle this sum. Like it has like indicator function of like supremo, this logarithmic solution, a Parabolic Anderson model properly scaled exceeding some value. So this is kind of the core thing that one needs to control. So what we do is that to control this, we come up with the comparison principle. And the thing that we compare this with this largest eigenvalue of this Anderson Hamiltonian. So you take this particular length of a box, And then within that box, we'll consider this with a Dirichlet boundary condition. We consider the largest eigenvalue of this Anderson Hamiltonian. We showed that this logarithm of the solution of this parabolic Anderson model, when scaled by t times this eigenvalue, like if you vary this this x argument x inside this solution of the parabolic Anderson model over this box of unit size, then this supremum would be almost surely equals to 1. So this kind of so it ultimately boils down to sort of like understanding this indicator function to something related to this eigenvalue of the parabolic Anderson model. So with this comparison principle, if you have to rewrite this whole sum, it would look something like this. Now it's kind of a slightly simpler form than whatever it was looking like before. So now one needs to understand how this how to tackle this kind of tail probability at this largest eigenvalue of the parabolic Anderson model, and as it turns out to be the case that one needs to study this kind of a large deviation type probabilities for this largest eigenvalue. And this is kind of a, again, like it needs some sort of like machinery which is not was the like which is kind of related to this previous techniques that to develop for large deviation theory. But again, like since this is an object which is coming from a system which is like not which is has some singular behavior, so it needs some sort of like a regularization techniques to study this large deviation probability. And but then like nonetheless we were able to kind of do it. So this is rather easy to done than like this studying this directly this solution of parabolic Anderson model. So this we are able to figure out this large deviation probability, plug that in here, and with kind of strong bound on this probability, one would be able to show this kind of this statement that this random sum would be finite almost surely. Okay, so now this lower bound. So as it turns out to be the case in many occasions, the proof of upper bound would be kind of easier, and proof of lower bound it would be kind of a bit harder. And this case is not exception. So, but then like one needs to come up with the correct notion or correct sort of ideas about how to prove this lower bound. One of the kind of like the way to do it is that to kind of resort to this idea of the thickness of a set. So we need to show that these upper level sets that we are considering are sufficiently thick. And what do we mean by that? A set E is theta thick if in this following figure, like so remember that while defining this Hausdorff dimension, we had this geometric figure, and we were kind of dividing it into growing squares, and there's this region between the squares. So there is this n plus 1h square and then nth square. So what we do is that we'll divide this shell region into squares of for smaller sizes. Now this time it would be of size e power n theta. And this geometric object E, geometric set E, would be called theta thick if for all n, the smaller set or smaller squares, like almost all of them has some point from E. And we claim, or we want this to happen for all n, like that's kind of an important part, almost all n. So if one can prove such thickness property, then there is an immediate lower bound for this kind of fractal dimension. One can prove that if theta is E is theta thick, then this macroscopic Hausdorff dimension would be just d times 1 minus theta, where d is the dimension of, or kind of space, dimension of the space where E is embedded. Okay, so what do we do is that, like again, like this has this lower bound proof like requires technicalities from different perspective, like one of the things that I mentioned, it needs some sort of regularization, as like some renormalization techniques that came out in like this stochastic PD for last 10 years. And just to summarize what kind of the things would have gone into this lower bound proof, we need an almost sure statement. So we need to show that this this set that we want to study is has some thickness. So we need to resort to this Borel-Cantor lemma in some way, and it needs some control on these probabilities, or like tail probabilities of the solution. And so this tail probabilities would come through like this comparison principle. So basically, it boils down to studying the tail probability of this largest eigenvalue. And this, as I said, like we were studying it in the upper bound, it also would be helpful in the lower bound. And but then this Borel-Cantor lemma in this particular occasion needs some sort of like local decoupling of the solution. And so you need to construct this, or study or construct a local proxy of the solution of the Parabolic Anderson model in this different size, in a far apart size. So this local proxy, construction of this local proxy would be done through this Feynman-Katz formula. And these two things would be put together to kind of like prove this associated, like the kind of Borel-Cantor lemma that proves this almost sure statement. Okay, so this is the proof of the lower bound, or how kind of this general idea behind this proof of the lower bound. Okay, so the plan is that, so I'll kind of mention the summary and this kind of future duration. And one thing that I probably would have 10 more minutes after this, or like, right. So to give you just like the idea about the challenges related to this problem, I'll show you some sort of challenges coming through like this Feynman-Katz formula, which probably like some of you have seen in different contexts. And then I'll kind of finish my talk. So the summary is that we have the exact value of the fractal dimension in 2 plus 1D and 3 plus 1D case. And using the tools that we develop for the fractal dimension, also we're able to prove some asymptotics. And in both these results, we were heavily using this regularity structure paracontrolled calculus. And it's probably the first instance where this regularity structure were able to show some kind of quantitative result of certain nature. Now, some of the future kind of direction that we're pursuing is this this complete localization kind of picture for Parabolic Anderson model, or Anderson model for dimension 2 and 3 for white noise case, which is still unknown. And for KPZ equation, it's not very far from this Parabolic Anderson model. This noise that we are using is just spatial white noise, at least for this problem. If you just make it a space-time white noise, you'll get close to this KPZ equation. So, and the critical dimension for the KPZ equation is this 2 plus 1D case. So, like one can study, like at least in a subcritical phase, some sort of like this fractal properties in this 2 plus 1D KPZ equation. In a separate works, I have some notion of this finite time intermittency for a system where which is critical. And so it would be sort of interesting to study, like in this finite time intermittency case, how to nail down this kind of multifractality for this models. Then one can study this anisotropic KPZ. But one thing I haven't noted here, but then I want to sort of mention it, is that the study of this multifractality, or which is kind of I showed you how it's related to this turbulence or like the intermittency, has actually been like started by Kolmogorov, and then it's kind of went. It lived like separate lives in a literature of physics, like different people, like different physicists, like have like different ways to kind of characterize it. But then this multifractality for like at least for the Navier-Stokes is a kind of a well-known kind of unproven result. So it would be kind of very interesting to kind of do this or prove some sort of multifractality for the stochastic Navier-Stokes, even for the case where it's not like a singular or like a you can study the moment. So it's not been done yet. So it's like would be interesting to kind of pursue that direction. So I'll have 10 minutes or 10 minutes, okay. So what I will do is that in the remaining 10 minutes, I'll show you this kind of a bit challenges associated to like studying this system, especially even like just to make sense of the solution of the system. So let me just give you the idea of how Feynman-Catch formula actually looks like in practice, and then the necessary modification that we have to do, at least for this case. So in general, if you want to study this solution of this parabolic Anderson model in a box started from, let's say, initial data phi, you're studying it in a box of center y and length epsilon L. So since it comes with a white noise, you need to regularize the system. And that's how people usually try to make sense of it. But then if you try to regularize it, it's sort of like it would be done in this following way. This is the noise part, if you kind of like, and then I restrict my noise in this box, and I also kind of mollify this noise with kind of convolving it with a kernel of bandwidth epsilon. And then I had to kind of subtract a constant to make it finite. And then you kind of integrate that with respect to the Brownian motion. So of this box. So this is the box. You're restricting the Brownian motion to lie in this box, and then you take this expectation with the law of the Brownian motion. It's, this noise part would make the thing random. Now the thing is, the challenge is that this part, even if you sort of kind of subtract this constant, this will still be blowing up in dimension 2 and 3. So you cannot actually pursue this kind of like this way of regularizing the system. Now, the alternative thing that we came up with, which kind of motivated from some of the these ideas that Koenig, Perkowski, and Van Zoylen was doing, but here, since we had to do it for 2 plus 1D and 3 plus 1D case, we had to do like slightly in a different way. So, so this is the representation that we have used, and you'll see just like in the representation, it just like became so complicated. So what I'm doing here is that like I'm replacing this exponential by a functional, which I'm going to write. We'll take a little bit more space here. But then there is I replace this Brownian motion by a diffusion, and this like a diffusion would have a drift, which kind of would be related to this d functional that I'm going to write. So this d functional, let me just write this one by one. This is okay. So this d functional has like this integral, and then there's like it has to sort of like one has to subtract some error term. But then I introduced two more things here, and this would be defined through in this following way. So this z y l epsilon is basically this 1 minus 1/2 times Laplacian inverse of the noise. And the y is defined in this following way. Take this eta 1/2 delta y l 1/2 gradient z y square gradient y l epsilon gradient z epsilon plus gradient y. Okay, so and then like this diffusion is just like this xt is just Brownian motion plus the drift. Drift is just gradient of z plus gradient of y. Now, why I'm doing this? So by this procedure, I got an expression where this z, where it has now like this z and y, and this has now a positive regularity. So it's easier to deal with than this noise that I had, which has this negative regularity. Now, how this magic happened, I went from a negative regularity object to a positive regularity object, and it happened through some trick called Grierson-Hauss theorem. And to apply this Grierson-Hauss theorem, one needs to sort of like put the structure like this. So that's why this weird kind of looking structure coming in. So and again, like this one thing. So there's subtle difference between 2 and 3 dimension. So in 2 dimension, this way I define this y, you don't need to keep this extra gradient of y square. You can still work with it. But in 3 dimension, again, there's the regularity of this noise became worse. So there, you need to sort of add this to kind of counter some kind of singular term. So that's sort of like the where, like at least this is kind of a one very small kind of window of challenges that I can show it to you. Like, but other it became more complicated. So I'll just if stop here, and I'm happy to have like more question related to this.
Questions?
Thank you. Do you set capital X sub 0 as small x here when you define the diffusion?
Oh, this is, okay, let me just write it down. This capital X is just like gradient of C plus gradient of eta y, eta times y, dt plus Brownian motion.
Initial?
Sorry?
Initial? You want to set an initial condition?
Oh, the initial condition. So it would be started at y.
Okay.
Yeah. Yeah. I think. Yeah. For probably like the integral representation would.
But your left hand side depends on small x, right? I can't see how small x appears on the right hand side.
Because this noise would be dependent on x.
Okay. Yeah, got it. Okay, thank you.
Any more question? If not, let's thank the speaker again.